Hello, and welcome back to another physics lesson. We are still on the subject called thermodynamics and on the unit on temperature and heat. So before we proceed with today's lesson, let us first review or recall the previous lessons. So you have learned about the zeroth law of thermodynamics, which is all about thermal equilibrium. So when two objects or bodies have the same temperature, then they are said to be in thermal equilibrium and vice versa. So you have also learned about the different temperature scales. So you have the Celsius and the Fahrenheit scales, which are degree scales. And you also have the Kelvin scale, which is an absolute temperature scale. So unlike the Celsius and Fahrenheit scales, which can have negative values, the Kelvin scale uh, is absolute. It has no negative value. So a 0 Kelvin temperature means it's absolute zero. So for this lesson, we will be discussing about thermal expansion. So what is the physics behind thermal expansion and what are the important applications? So thermal expansion is basically the change in size of an object due to a change in temperature. So of course, if only the size of the object changes and its mass stays the same, then its density will also change. So an increase in temperature usually means expansion. And when an object expands, its size gets bigger, its mass remains the same, then its density will become smaller because density is inversely proportional to uh, volume or the size. So this is clearly depicted in your usual thermometer. So the liquid or the material inside your thermometer, when you heat it, you put it against your hot body, that material will expand. So the thermometer is actually calibrated in such a way that the length of the expansion will correspond to a certain temperature change. The reverse, if you decrease the temperature, you will notice that this line here, this red line here, the thermometer will also get smaller or will contract. So a normal object, when heated or when you increase its temperature, it will actually get bigger. But if you contract it, if you make its temperature uh, lower, then it will contract or become smaller. So in the uh, atomic or molecular picture, what happens when you increase the temperature is just the average distance between the atoms or between the molecules increases. But the size of the atoms doesn't change. So please disregard the change in size in my picture. So the atom should stay the same size, but the distance between the atoms changes. So that is the molecular or atomic picture of thermal expansion. So this means that if you have an object and if you increase the temperature of that object, the distance between the atoms or molecules composing that object will actually increase if you increase its temperature. Therefore, the object will expand. Similarly, if your object has a hole in it, then the atoms or molecules at the edges of this hole, uh, their distance will also increase. Therefore, the hole will also expand. So that is the principle of thermal expansion. So increasing the temperature, it will get bigger, or decreasing its temperature, it will become smaller. That is the normal behavior of objects when you increase or decrease the temperatures. So there are two types of thermal expansion, and we will discuss both. So we'll start first with linear expansion. This happens when only the length of the object changes due to changes in temperature. So similarly, we have introduced earlier the concept of this old school thermometer. So the length of the material inside this thermometer will change linearly, or its length will change upon changes in temperature. So if that happens, if that is the case, that only the length changes, then you use the concept of linear expansion. So mostly in thermometers, the liquid inside your thermometer is mercury, but modern thermometers usually don't use mercury anymore. So if at an initial temperature T sub 0 or T naught, the length of your object is L naught or L sub 0. And when you change the temperature, say you increase its temperature to a certain temperature T, and its length now increases. So this change in length, the difference between the final length and the initial length, so that is the change in length, is given by this equation. So this is now the mathematical expression of linear thermal expansion. So the change in length, the final length minus the initial length, is equal to some constant here, alpha, which is what we call the coefficient of linear expansion. L naught or L sub 0 is the initial length. Delta T is the change in temperature. So this is final temperature minus the initial temperature. So you see as delta symbol, it means change, and change is usually final minus initial. So different materials have different coefficients of linear expansion. So for instance, if you have aluminum, the coefficient of linear expansion, which is alpha, is 2.4 times 10 to the negative 5 Kelvin inverse or Celsius degree inverse. So Kelvin inverse and Celsius degree inverse are similar units when it comes to change in temperature. Please don't be confused with the unit called Celsius degree. Some physicists or scientists use this notation that if you get the difference between two temperatures in degrees Celsius, the final unit is, instead of degrees Celsius, you get Celsius degree. So if you saw a unit called Celsius degree, that just means it's a change in temperature in degrees in Celsius. So this also means that the change in temperature in degrees Kelvin and in Celsius are just the same. Okay, so from the table or from the equation, you will notice that alpha is directly proportional to the change in length, meaning the larger the alpha, the greater the change in length. So in this table here, we see that in this list, aluminum has the highest value of alpha. Therefore, uh, if you have uh, a certain uh, length of all of these materials, they start at an initial length L sub 0, and then you heat them, all of them, to a final temperature, then you will notice that the aluminum, since it has the highest value of alpha in this table here, it will have the longest uh, change in length. It will be the longest among these uh, materials here, provided that you start with the same length. All of these materials start at the same length. So the greater the alpha, the greater the change in length. So this means that aluminum will have a greater change in length as compared to brass if you heat them simultaneously at the same time, starting from the same length. Okay. So a change in length A positive change in length means expansion, and a negative change in length means contraction. So you will get positive and negative values of changes in length here. So positive just means it expands. Negative means it contracts or it becomes shorter. So let's have an example. So you must have noticed in our bridges that they have what they call expansion joints. So there's like a teeth-like structures. So those are expansion joints. So the purpose of these expansion joints is to accommodate or to take into account the changes in length that result from thermal expansion of the bridge. So a bridge has a steel bed. So the steel, for example, in this problem, the steel bed of a suspension bridge is 200 meters long at 20 degrees Celsius. So 200 meters is our initial length. 20 degrees Celsius is our initial temperature. So how much will it expand during a hot day of 40 degrees Celsius? Or how much will it contract on a cold day of negative 30 degrees Celsius? So for the hot day, 40 degrees Celsius. So 40 degrees Celsius is our final temperature. So we use the formula for the change in length. So this is steel, and steel has an alpha of 1.2 times 10 to negative 5 Kelvin inverse, or we can use the unit called Celsius degree inverse. So its initial length, L sub 0, is 200 meters. And the change in temperature, this is final temperature minus initial temperature. So in this case, for the hot day, 40 degrees Celsius is the final temperature, minus the initial temperature is 20 degrees Celsius. So you will notice that the unit for this difference in temperature is Celsius degree. So 40 degrees Celsius minus 20 degrees Celsius is equal to 20 Celsius degree. And the unit of this is Celsius degree inverse, so therefore the two units of this will cancel each other out. The final unit will be meters. Since our variable or our quantity is change in length, and the standard unit for length is meters. So you will get a change in length of 0.048 meters, but in order to appreciate this value, we need to convert this into a more layman value, or a more appreciable value, which is in centimeters. So in centimeters, this is 4.8 centimeters. So 4.8 centimeters is actually almost 2 inches. So almost 2 inches. That is the length of that's 4.8 centimeters. So meaning on a hot day of 40 degrees Celsius, the bridge will increase by almost 2 inches. So that's the reason why you need expansion joints to take into account this expansion. Because if you don't put an expansion joint, what will happen is instead of expanding, your bridge will buckle because there's no room for expansion. So you need an expansion joint. So usually on a normal day, there's a gap in your expansion joint, and on a hot day, the gap will become smaller, or the gap will disappear on a hot day. It's because the bridge will expand. So that's for the hot day of 40 degrees Celsius. Similarly, you use the same equation for the cold day. The only difference is that the final temperature, since it's a cold day, the final temperature is negative 30 degrees Celsius. So you can, during the substitution part in your solution, you can just omit the units as long as you write the final units. So the unit here is Celsius degree inverse, and it will cancel out of the unit of this one, negative 30 minus 20 degrees Celsius, and the unit of that is Celsius degree. So the final unit is in meters. So for a cold day of negative 30 degrees Celsius, the expansion, or sorry, the contraction rather, because this is negative means contraction, is 0.12 meters. Or in the centimeters, that is negative 12 centimeters. So negative 12 centimeters is almost 5 inches. That's actually a very big, almost 5 inches is a very big gap. So you need to take into account the contraction. So luckily for us in the Philippines, we don't have cold days, negative 30 degrees Celsius temperatures. So our engineers building our bridges don't need to take into account the contraction, only the expansion. But if you are living in a place where there are winter seasons and summer seasons, then you need to take into account both the expansion and the contraction. That one. So yes. Okay. So the second type of thermal expansion is volume expansion, when the whole volume or size of the material changes. So suppose you have a material with an initial volume V sub 0, initial temperature of V sub 0, you increase its temperature to a final temperature of T, and it has now a final volume of V. So the change in volume, the final volume minus the initial volume, V minus V naught, or delta V, that is V minus V naught, that's a change in volume, is given by beta V naught delta T. So beta is another coefficient of expansion. This is now what we call the coefficient of volume expansion. So alpha is the coefficient of linear expansion, beta is the coefficient of volume expansion. So each materials has two sets of coefficient of expansion. Aluminum has a coefficient of linear expansion, and it also has a coefficient of volume expansion. So it has two sets, or yeah, it has two sets of coefficient of expansion. So different materials have different coefficient of expansions, volume expansion, and similar with linear expansion, the larger the beta, the larger the change in volume, since these two quantities are directly proportional. And a positive change in volume means expansion, a negative change in volume means contraction. So it's volume contraction, the negative expansion. Okay. So in this list here, aluminum has the highest coefficient of volume expansion. So meaning, if you have a box of aluminum and a box of, say, steel, and they have the same initial volume and initial temperature, and if you heat them simultaneously, then aluminum will have a much larger change in volume, or the aluminum box will become more larger or much larger than the steel box. So that's what the coefficient of expansion means. The higher the value of coefficient of expansion, the higher the expansion. So let's compare the table for the coefficients of linear expansion and volume expansion, so alpha and beta. So you will notice a pattern here. For alpha, it's for aluminum, its alpha is 2.4 times 10 to the negative 5 Kelvin inverse or Celsius degree inverse, but its beta is 7.2. For brass, it's 2. Its alpha is 2. Its beta is 6. So the pattern is the beta, the coefficient of volume expansion of a material, is actually just three times the alpha. So if you're only given the alpha, but you need the beta of that material because the expansion is volume, then you just multiply by 3. And if you are only given the beta and you need the alpha, then you just divide the beta by 3 to get the alpha. Okay. So let's have an example on volume expansion. So this is an expanding metal sphere. So suppose you have a solid aluminum sphere with diameter of 10 centimeters. What will be its change in volume if it is heated from 30 degrees Celsius to 600 degrees Celsius? So before we can use the formula here for volume expansion, we first need to know what is the initial volume of our aluminum sphere, because we are only given the diameter. So if you have a sphere, the diameter of a sphere, or actually a circle or a sphere, is actually twice its radius. So meaning, if the Diameter of this sphere is 10 centimeter. Therefore, its radius is one half of this, which is 5 centimeters. The volume of a sphere is actually 4/3 pi times the radius cubed. So this is the formula of the volume of a sphere. So therefore, we can now solve for the initial volume of our solid aluminum sphere with diameter 10 centimeters. So 4/3 pi initial radius cube. So 4/3 pi, the initial radius is 5 centimeter. We need to convert that into meters, so 0.05 meters cube. And you get this value. So you will notice that, by the way, the unit is meter cube because this is volume, cubic meters. That is the standard unit for volume. So you will notice here that I did not round off my values because this is still an initial calculation. This is not the final answer. So during your problem solving solution, please do not round off your initial calculations, only round off on the final values or the final answers. So we can now then use the formula for the volume expansion. So the change in volume is beta initial volume change in temperature. So you will get the beta of aluminum is 7.2 times 10 to the negative 5 Celsius degree inverse. You will notice that I omitted the unit here because the final unit is, I already placed the final unit here, which is meter cube. So this is the initial volume, and this is the change in temperature. Final is 600 minus the initial is 30. And you will get a value of 2.15 times 10 to the negative 5 cubic meters. But usually cubic meters cannot be appreciated because cubic meters is for very large volumes. It is appreciable if you have a very large volume. But in this case, this is 10 to the negative 5. This is a very small volume. So for very small volume, we need to convert it into a more appreciable unit. So such as the centimeter cube or the centimeter cube or cc. Generally, or in layman's term, it's cc or centimeter cube or cc. And 1 cc or 1 centimeter cube is just equivalent to 1 ml. So in terms of cc or centimeter cube or ml, it's 21.4 ml. Or rather, I guess this is 21.5. Sorry, this is 21.5 ml, not 21.4, because this is, I just rounded this off. This is 21.5 ml. Okay. So last example for this topic. So suppose you have a glass flask, 200 ml glass flask, and it's filled to the brim or to the top with mercury at 20 degrees Celsius. So how much mercury overflows when the temperature of the system is increased to 100 degrees Celsius? So you are given the alpha of the glass and the beta of the mercury. So this is an example of volume expansion. So the volume of the glass and the volume of the mercury will both expand when you heat them from 20 degrees Celsius to 100 degrees Celsius. But you will notice that you need the beta for glass, so you just need to multiply the alpha of the glass by 3 to get the beta of the glass. So 0.40 times 3, you will get 1.2 or 1.20. But if you compare that to the beta of mercury, it's 18. So mercury has a higher beta, which means it will expand, the amount of expansion of mercury will be larger compared to the glass. That is the reason why the title of this problem is mercury overflow. So the mercury will now overflow from this glass flask because its expansion is much larger as compared to the glass. So it will expand much larger as compared to the glass. So let's calculate the volume expansion for mercury. So it's just the beta of mercury, initial volume of mercury, the change in temperature. In this case, both the glass and mercury have the same initial volume, and they also have the same change in temperature. That's 100 minus 20. And you will get a value of, so I already converted this to ml, so you have 2.88 ml or milliliters. So you do the same for the glass. So again, you need the beta of the glass, but you're only given the alpha, so you need to multiply the alpha by 3. So they have the same initial volume and change in temperature. And the final unit, sorry, I forgot to place the final unit here. There should be a unit ml here. There should be a unit ml here. So the final unit or the final expansion for the glass is 0.19 ml. So you will notice the difference here. So the mercury will expand by 2.88 ml and the glass will expand by only 0.19 ml. So take note, they start from 200 ml. So therefore, the mercury at 100 degrees Celsius will now become 202.88 because it now expands by 2.88. So it will now become 202.88 ml, and your glass from 200 ml, it will now become 200.19 ml. So the overflow is just the difference of the two volumes or the two change in volumes. Change in volume of the mercury minus the change in volume of the glass. So you subtract this two and you will get 2.69 ml. So this is now the overflow. So typically, most metals expand faster as compared to glass. So if you experience this one, if you experience a lid on a metal lid or a metal cup on a glass na jar, this usually happens when you freeze this one and you put them in the freezer. So the metal lid or the metal cup will get stuck. So in order to unstuck this one, so you just need to hit the two. So you put hot water on this system, and since the metal will expand faster as compared to the glass, then the metal lid will get loosened, and you can now open this easily. So that is how you apply thermal expansion in a real life problem. So before we end this lesson, let us discuss the thermal expansion of water, because there is uh, an abnormal behavior of water with respect to thermal expansion. So above 4 degrees Celsius, when you decrease the temperature of water, it's normal, it will contract. And if you if you increase its temperature, it will expand. So below 0 degrees Celsius, if you increase the temperature of ice, so say for instance from -5 to -3, of course ice will expand. And if you decrease the temperature further, say from 0 to -5 degrees Celsius, ice will contract. So these are normal behaviors in this region. The abnormal behavior of water comes in this region here, from 0 degrees Celsius to 4 degrees Celsius. Now, if you increase the temperature of ice or water from 0 degrees Celsius to 4 degrees Celsius, so instead of expanding, it will actually contract. It will become more dense. And if you decrease the temperature of water from 4 degrees Celsius to 0 degrees Celsius, instead of contracting, becoming smaller, it will actually expand and become ice. So when it expands, it will become less dense. So this region is the anomalous region, or this explains the anomalous behavior of water in this region from 0 degrees Celsius to 4 degrees Celsius. So ice at 0 degrees Celsius is actually less dense as compared to water. So that is why that's the reason why ice floats on water, because it's less dense than water. So anything that is less dense than water will float on the surface of the water. And this is also the reason why a glass bottle with water inside it will break if you place them inside a freezer, because the glass container or the glass bottle will contract, but the water, which becomes ice, will expand. So and if your container is glass, then it will break. So I don't know if you have experienced that, if you have experienced this, but you can try if you want. You can place a glass. Of course, it should be a closed, say, soft drinks bottle, A glass soft drinks bottle, if you place that in the freezer, that will definitely break. And this is also the reason why living things in water survive. Because uh, since ice is denser than water, then the first part to freeze in an ocean or in a lake will be the top surface. And since the top surface is already frozen, it becomes a shield now. For it becomes a shield from the outside environment, from the colder outside environment, and the water below the surface will no longer freeze as long as the temperature outside doesn't get colder enough, doesn't get uh, colder. So this is the reason why fishes and other living things underwater survive during winter seasons, especially in those areas where there is winter. So such as lakes. So you see frozen lakes, frozen oceans, but under those frozen surface is just water. Okay. So that is it for thermal expansion. And I hope you learned something about uh, thermal expansion, and I will see you again in the next lesson. So goodbye.